With the rise of encrypted user-generated content, participatory networking has become essential for the end users to assist in network management to get the improved quality of service for their applications. Since users interact with the various multimedia applications on their smart devices, we need to understand the ongoing multimedia activity on a device. We call this multimedia context. A multimedia context defines whether a user or device is producing or consuming content or engaged in a conversation. My name is Mohammad Haq. I'm a postdoctoral researcher at the University of Helsinki. I'm going to present our accepted paper titled Sensing Multimedia Contexts on Mobile Devices. This research is conducted in collaboration with the Georgia Institute of Technology and Hong Kong University of Science and Technology. Now, in order to identify the multimedia contexts, we seek the answers of the following questions. First, what are the content types offered by various multimedia applications? And next is how do the users interact with different multimedia applications? Third is which IO devices are utilized during such interactions on smart devices? And finally, what are the states of these IO devices when users interact with the multimedia applications? So we first actually classify different multimedia applications according to their purpose and define three basic multimedia contexts as shown in this figure. Those are like multimedia production, and then multimedia consumption and conversational multimedia. Next, we classify or separate these media contexts according to their content type, like audio and video. And finally, we do another step according to the source or destination of the content. For example, some recording application would record the audio or video on their local devices. On the other hand, a Periscope-like application would broadcast the content to the participant or consumer of the contents. And at the bottom, finally, you would have around 11 multimedia contexts. Now we will investigate the conversational multimedia contexts. This figure shows the states of IO devices during a VIP conversation with WhatsApp, and the right-hand side figure shows how the states changes during the audio conversation and the video conversation. In the left figure, we can see that the conversation is initiated at T0, and all the required IO devices like speaker and microphone are also initialized at the same time. And the display is turned off at T1. The user turns on the display again at T2, and the call is terminated at T3. During conversation, multiple traffic flows are initiated. The TCP flow carries mostly the signal in traffic, and UDP flow carries the multimedia content. The audio conversation mostly have bit rates between 70 to 22 kbps. On the other hand, VIP conversations have bit rates around few hundred kilobits per second. GSM and VoLTE calls also require a microphone and speaker together. The figure on the right hand side again shows the call transitions from audio to video and video to audio. Note that this actually depends on the applications, as the applications may not allow to switch to video in the middle of a audio conversation. On the other hand, when an end user plays multimedia content from local storage or streams from a remote service provider, the device is in a media consumption context. These figures show the streaming context for tune-in application and 4 different multimedia consumption contexts. The left figure shows that only display speaker and network activities begin when a tune-in audio streaming session starts at T0. The display is turned off at T1 and turned on again at T2. The user terminates the streaming session at T3. Tune-in initiates multiple TCP flows as soon as the playback begins. The bitrates of tuning audio streams vary between 24 to 320 kilobit per second. These streams are basically constant bitrate streams. However, some applications can have on-off pattern in their network traffic. The right figure shows four different multimedia consumption contexts based on the source of the content and the content type like audio and video. In contrast, a mobile device is in a production context when the application records audio or video on local storage or broadcasts live to some remote consumers. This figure shows the states of the IO devices during a live video broadcasting session of Periscope. The live broadcast begins at T0 and the application initializes camera and microphone. The output device display is also used and the data transmission begins. The broadcast terminates at T1. Periscope initializes to the 8 TCP connections. However, only one of the flow creates the multimedia traffic. We observe that the uplink bitrate of Periscope is 450 kilobits per second, and the audio bitrate is around 120 kilobit per second. It is expected that a user would involved with one kind of multimedia activity on his or her smart devices. However, the question is whether it is possible to have multiple multimedia context at the same time on a smart device. We carried a number of experiments and this table actually shows the results. We can see that two media production applications cannot be played together on a single screen device. Audio and video content cannot be recorded at the same time by two separate applications. We also in fact tried to record audio via default voice recording application, and the recorder stops as soon as Periscope starts broadcasting. Nexus 6 does not allow to record or broadcast media when another streaming application is running. For example, it is not possible to run an audio recording application in the background and streaming via YouTube or TuneIn in the foreground. In this case, the audio recording terminates as soon as the player initializes the required sensors or IO devices. Similarly, recording application cannot be played during a VoIP call. Nevertheless, we are able to stream audio in the presence of a VoIP call in a single screen device. Next, based on our observation, we propose a multimedia context sensing algorithm called MEDIASENSE. MEDIASENSE scans the states of 5 IO devices shown in the figure on the left and fuses them together to inform the media context or multimedia context. We implement MEDIASENSE algorithm as a user-level service for Android devices. It runs as a background service and looks for multimedia contexts periodically at 2 hours. Whenever one or more media IO devices change states, MEDIASENSE initiates a new multimedia context. It first checks whether the media context is consumption or production or conversational with the help of mic and speaker. Then it decides whether the content is audio or video with the help of camera and display. In the implementation, I actually use standard Android APIs to detect these contexts. Then it finds a particular feature from the traffic stat in uplink or both directions to separate IP-based context from the local media context. Note that MEDIASENSE doesn't compute all the feature in this table for a particular media context. It rather computes media-specific features. For example, for uplink audio or video broadcasts, it considers a minimum bitrate of 8 kbps in uplink direction. Similarly, for conversational media, it considers 8 kbps bits in both uplink and downlink directions. In the case of multimedia streaming, it considers the amount of downloaded bytes during the first 10 or 15 seconds of conversation. This is called its fast start bytes. Finally, we evaluated the performance of MediaSense in identifying 11 media contexts from 12 different multimedia applications. Uh, for all the 12 multimedia applications, there were 80 media consumption sessions, 120 conversation context, and 80 media consumption context. The duration of each session was 60 to 90 seconds. The media sessions for the same application and media dive were executed after every 1 minute. This figure shows that MediaSense separates the top-level 3 media contexts accurately, and so the second-level media context with the help of camera and display. It classified multi-call as GSM as multi-traffic do not follow the standard TCP/IP stack. Note that MediaSense Fast detects the media consumption context as video, since the display is active initially in either audio and video scenarios. Therefore, audio consumption contexts are initially detected as video um, context. Then, after 50 seconds of playback, we turned off the display and MediaSense accurately detected the audio context. However, MediaSense suffered from errors in the presence of local media consumption applications. Among 20 sessions, the algorithm classified 3 sessions as audio streaming. Similarly, local video playback sessions were also classified as video streaming as smartphone updated some applications in the background during playback. Finally, MediaSense also measured the duration of 280 media sessions accurately. Multimedia contexts enable different energy optimization for mobile devices. For example, traffic aggregation, computation offloading, and background traffic scheduling. MediaSense can be used to identify various multimedia traffic in real time on mobile devices. Therefore, multimedia traffic classification by the service providers or mobile operators can be offloaded to mobile devices. It also can verify the QoS requirements of these multimedia applications and enable context-aware source routing. Thank you, and now I can take the questions.